Welcome to the 7th lecture in dynamics. We are in chapter 12, and today we will most likely start section 12.2, but before we do, I'm going to work some of the homework problems for you, or at least get you set up so that you can take a look at how the attack on these problems will be and ask any questions that you have about the execution of the problem. So having said that, the first requested problem that I have is for problem 12.2. This is dandy. I don't know if this is going to come up or not. There, it's going to come up. All right, so 12.2, while the system is coming up a little bit, there we go, is about a block and rope and pulley system, and trying to analyze to find out what's going on in terms of this motion. So it builds on problem 12.13. Signal just went off again. I may have to just start this vodcast over again if I can't make this happen. Now this should be right. There we go. All right, I'm going to try one. Oh, the document cam. We're going to do this, and then we're going to do this. Maybe? Yay, there we are. All right, we're functioning. We've got the technology going. All right, so first of all, it refers back to 12.13, so I'm going to read 12.13 and 12.14 as I draw this picture and we start to do our analysis. Now, those of you that are here, please, if you have any questions while I'm drawing, please interrupt me because I would like to explain it in a stepwise fashion. All right, so problem 12.13 and 14 refer to this diagram. And we basically have an inclined plane that is at a 30-degree angle with the horizontal. On that inclined plane, I have a block that weighs 200 pounds. The block is attached to a rope that goes over a pulley and supports another block that has a weight of 350 pounds. And the cable is ultimately attached to the ceiling. All right, so 12.13 says the two blocks shown are originally at rest. That means V0 equals 0. Neglecting the masses of the pulleys, now we don't get to neglect the effect of friction now in 14, but initially we got to to not pay attention to the friction. Now we have to include friction in our analysis. Determine the acceleration of each block. So we want to know the acceleration. Call this A and this B. So we want to find the acceleration of A, and we want to find the acceleration of B, and we want to find the tension in the cable. All right. Now, in problem 12.14, we're told that this block has a coefficient of static friction of 0.25 and a coefficient of kinetic friction of 2.0. All right, so that's a good time to think about what's going on here. What does that mean? Well, the coefficient of static friction talks about the coefficient that it will take to get the block moving. So in other words, if it doesn't exceed that number, if you don't get a force upward, for example, on the plane, you're not going to make the block move at all. You're just going to pull on it, but it's sticky to the inclined plane. So once it starts moving, the coefficient of kinetic friction comes into play, which is less. And typically, almost always, unless you have some weird material, the coefficient of kinetic friction is less because, in general, it is harder to get an object moving than it is to keep it moving. So the force of friction is a little bit less. So the first thing I would do with this problem, I'd say this block has 200 pounds, a weight of 200 pounds, and this block has a weight of 350 pounds. I really don't know initially if it's going to move down the plane or up the plane, but because this is heavier, I suspect it's going to pull the block up the plane. So I'm going to run with that anyway. Now, if that is incorrect, it will come out in the math. But once you draw your picture and you decide on your direction of motion, stay with that picture even if you find out that it is incorrect. If it is incorrect, your numbers will come out negative, and then you'll know at that point. But if you draw a picture and then halfway through change your math, then the picture and the math don't go together, and your answers are just going to be weird, and they're not going to be correct. So draw a picture, stick with it, move on. All right, so I'm going to say that the motion, the acceleration of block A, is going to be up the plane. That means that if this rope, part of the rope shortens, this part is going to lengthen, and that means that the acceleration of block B is going to be down the plane, doesn't it? Just to start. The other thing is, if my acceleration is up the plane, my frictional force between the block and the incline is going to be down the plane because the friction opposes the direction of motion. All right, so if I were to look at this and do a complete detailed analysis, I would do 3 small free body diagrams. One of them, let me just write that out, 3, it's almost like an exploded view, but I'll just say a free body diagram. The first one is the 200-pound block. The next is the cable between the blocks. And finally, it's going to be the 350-pound block. And all 3 of those will work together. So I'll draw a small free body diagram of each, and then I'll see how the variables relate to each other. Okay? So let's start with the 350-pound block. Well, let's start with the cable, first of all. All right? If I look at this and I call this the tension on, I don't know how to say that. All right. If I look at that, if this is the tension, when it goes around the pulley, whatever the magnitude of tension is, this is going to be the same value, isn't it? In other words, all that the pulley does is change the direction of that force. It does not change its magnitude. And similarly here. All right. So what that means is that this block is being pulled up, the way I have it drawn, with 2t force, a force of 2 times the tension, and this block is being pulled up the plane with a force of 1 times the tension. Okay, so that's going to help me, that's this part right here. That's going to help me relate the 200-pound block to the 350-pound block. So for the 350-pound block, I have the weight, which is 350 pounds, pulling it down. I have 2 times the tension pulling it up. And when I say the summation of forces in the y direction equals 0, and I assume that my y up is equal to 0, I can say 2t minus the weight is equal to the mass of the block times the acceleration of that block B. So here's my first equation. Now, the other thing, I guess before I get into that, let's look at the acceleration of A in relationship to the acceleration of B. Well, once again, going back to this cable, if this cable moves upward, in other words, if the x of block A moves upward 1 unit, how far down is block B going to go? It's going to be a half a unit, is right. So x of A then is equal to 2 times x of B. In other words, this block moves up twice as far as this moves down because of the configuration of the cables. If I take the first derivative, then I can say the velocity of A is equal to 2 times the velocity of B. And last but not least, I can say that the acceleration of A is equal to 2 times the acceleration of B. So this is going to tie this equation, acceleration of block B, into the acceleration of block A. All right, so I've kind of saved the best for last because the 200-pound block has the more complicated analysis. And as a technique, I'm going to choose my axes to be along the block. Now you can do this in a standard XY coordinate system, but everything then is going to break into components. The friction is going to break into components. The normal force is going to break into components. The tension is going to break into components. So it's much easier in general when you have an inclined plane to make one of the axes parallel and the other axis perpendicular to the block, to the surface of contact between the inclined plane and the block. All right, so what do I have going on for forces here? Well, I have a 200-pound block, so that means that we have the weight acting down. I also have the force of friction acting this way, and I have this thing called the normal force, which I'm going to talk about a little bit for just a minute. N equals the normal force. The normal force is the force that the plane exerts on the block. And so it is always perpendicular to the surface of contact. It's always perpendicular to the surface of contact. All right. And the word normal actually doesn't mean as the opposite of abnormal. The word normal actually means, in this expression, perpendicular. So we're talking about a perpendicular force. Just like if you remember when we were talking about the circle, we had a tangential component of velocity and a tangential force, and then we had a normal force. The E sub n vector is directed perpendicular to the tangential. So normal is just an old-fashioned term for perpendicular. All right, so if I do my block and I orient my axes like this, the first thing I would like to do is to do my forces in the y prime direction. And I have, in the y prime direction, I have the normal force acting upward, which I'm considering positive. And then I don't have the entire weight. I have some component of weight. So in other words, my weight is still going to be vertically directed downward. But in that direction, in the normal direction, I have some component of weight acting downward, minus weight in the normal direction, or in the y prime direction, let's call it that. And in the y prime direction, which is perpendicular to the plane, I don't have any acceleration, right? So this is going to equal the mass times the acceleration in the normal direction, which is equal to 0. Now, in the x prime direction, I'm going to have to work with this a little bit more, but I want to go ahead and finish this off. In the x prime direction, I have a tension pulling it up the plane, which I'm considering positive. I have a frictional force pulling it down the plane. And I have a component of weight. And if you look at the arrow, it's going to be pulling it down the plane as well, only this is going to be in the x prime direction. And this is going to equal mass times the acceleration of that block in the x prime direction, which, as you can see from our original diagram, is just equal to the acceleration of A. All right, so now what is left to us is to resolve the weight into an x prime and a y prime component. We're told that this angle is 30 degrees. Well, if you consider this surface is perpendicular to this, and horizontal is perpendicular to vertical, if this angle is 30 degrees, this angle has to be 30 degrees as well, doesn't it? Just doing a little bit of trig. So that means that in the y prime direction, this is going to be equal to the weight, and it's the adjacent, so that's the cosine of 30 degrees equals 0. And here, the force of friction is equal to mu. We haven't decided if it's mu s or mu n yet. We're just going to say mu times the normal force, which is to be determined up here, minus the weight in the x prime direction, which is going to be the weight times the sine of 30 degrees, is equal to the mass, and that's the mass of block A, times the acceleration of block A. All right, so we have some good stuff to work with here. Now, the first thing that we really have to do, if this block doesn't move, there's no point in doing the rest of the problem, right? So, is the block going to move? So that's the first question we have to ask. And that means, are we going to overcome the coefficient? Let me do it up here. Sorry, let me see where we are. So first ask, will the block move? Because if it doesn't move, analysis stops. How fast is it going? It's not. How fast is the other block going? It's not, right? So those are the answers. But we have to decide if the block will move. Well, what will cause it to move is if the force of friction is actually overcome by the tension, all right? And that would be the force of static friction, so that would be mu s times n. If this is less than or equal to the tension, then it will move. So we can test this out. We don't have all of our stuff, but we can think about it this way. Our mu s value was given as being 0.25. We know that the normal force is the weight, which is 200 pounds, times the cosine of 30 degrees. And is that less than or equal to the tension? We're not going to know that till we do the next part of the problem. But we'll have that standard so that when we do the next part of the problem, if we don't overcome that, then there's no movement. Okay? All right, so let's just get that number, which we can also use right here. Or we can't, because we have to use the other coefficient. Never mind. No, we can do that. So here we get 0.25 times 200 times the cosine of 30 degrees, and that equals 43.3 pounds is less than tension. This is the criteria for it to move. So in other words, if the tension that we calculate is greater than 43 pounds, 43.3 pounds, then it will move. If we calculate it and it's less, then we don't have a deal at all. Well, I guess we have a deal. We have a static situation with tension. All right, so let's proceed here. The first thing I want to do then is to find my normal force. So normal force is equal to weight times the cosine of 30 degrees. That's 200 times the cosine of 30, which we just found is 43.3 pounds. So the normal force between the surface and this 200-pound object, the normal force is 43.3 pounds. All right, we can use that in this equation. We're still going to have more unknowns but now we're going to assume motion. My tension now is going to equal mu k, which is 0.2. I'm assuming this is true, that this is happening, times my normal force, which is 43.3, minus the weight, which is 200 pounds, times the sine of 30 degrees, is equal to the mass of the object, which if you remember from Newton's second law, force is equal to mass times acceleration. That means that weight is equal to mass times gravity. Mass is equal to weight divided by gravity. So since I'm in pounds, I can write the mass of A as being 200 pounds over the acceleration of gravity, 32.2, and that will be in slugs times the acceleration of A. Okay, so I'm going to simplify this equation. T minus 0.2 times 43.3. That's 8.66 minus 200 times the sine of 30 is 100 equals 200 over 32.2, which is 6.2 slugs times the acceleration of A. And then if I just do that little 8.66 minus 100, we get T. Are those both negative? Yeah, they are. Okay, I just saw it backward in my head. So it's 108.66 equals 6.2 acceleration of A. All right, so now we have a useful equation. But we have two unknowns. So that means that we need to find another equation, because if you have two unknowns, you need to have two equations. Well, we started it back here, didn't we? All right, so I can use this equation, 2t minus the weight of this block, which is 350 pounds, equals the mass, 350 over 32.2, times the acceleration of B. So here I have acceleration A, here I have acceleration of B, but I also know that they relate to each other based on the pulleys. So the acceleration of A is equal to 2 times the acceleration of B. Or I could say that the acceleration of B is equal to 1/2 the acceleration of A. So if I were to simplify this, I could say 2t minus 350 pounds equals 350 over 32.2 times, instead of writing the acceleration of B, I'm going to write the acceleration of A over 2. All right. So I'm going to simplify this equation. 2t minus 350 equals, I have 350 divided by 32.2 divided again by 2. So this coefficient is 5.435 A sub A. Now I have two useful equations in the same two unknowns, so I can combine those in any way I would like. I'm going to go ahead, now you could solve this for A sub A, solve this for A sub A, or solve either of these equations for T, and then substitute. This looks a little easier to me just because the T is just out there by itself. So I would write this as T is equal to 108.66 plus 6.2 A sub A. And then I would substitute that into here. Oops. And so I get 2 times 108.66 plus 6.2 A sub A. That's my tension. Minus 350 equals 5.435 A sub A. So 2 times 108.66, I have to distribute that through. So this is 217.32 plus 12.4, oops, A sub A minus 350 equals 5.435 A sub A. So I have 217 minus 350. So this is a negative 132.68. Then I bring this over to that side and it becomes a negative. So I have 5.435 as the coefficient of A sub A, and I subtract from that 12.4. So over here I get negative 6.965 A sub A. So all I have to do is divide through 695, like that. And so I take this and I have times 132.68. Negative over negative is positive. 19.05, and I've been consistent with my units, feet per second squared, is equal to a sub a. So my first answer pops out, doesn't it? All right, so if a sub a is that, I further know it wanted me to, I want to have a sub a. That's one of my answers. Oops, it's my original sheet. I also need a sub b and t. So we know that a sub b is equal to 1/2 a sub a. So I just take that value, divide it by 2, and my acceleration of b is 9.52 feet per second squared. And then last but not least, we need the tension. And none of the equations look wretched at this point.
Is this for 12.13?
Use 12.14?
Yeah.
Yeah, it's 12.14.
This?
Do you have a different version of the book? Which is it a similar problem? Is it an inclined plane problem?
Yeah.
Okay, then I've allowed students to use different versions of the book. So these are the numbers that my version of the book has. If yours has a different version, the work is going to be the same. It's just going to be slightly different. And I did that for cost, just because the books, the new editions of the books are so expensive that I would prefer that people have more leeway. But yeah, so when you do that once in a while, the numbers are not going to be exactly the same. But the work in every case should be the same.
Okay.
All right? So I should have checked to see which version you had before I started doing that, Jenna. But still, the principles are still the way it works. So this is 12.14 with friction. Okay? So then anyway, the last thing would be to find the tension. And we can use any of the equations. So this is another good case for staying organized. But I know that T minus 108.66 equals 6.2 a sub a. So I'm just going to bring 108.66 over to the other side of the equation and add 6.2 times a sub a. So my tension is 108.66 plus 6.2 times a sub a, which is 19.05. So my tension then is, if I take 19.05 and I multiply it by 6.2 and I add 108.66, my tension is, sorry about this, got to do this again. 2 times 19.05 plus 108.66. My tension is 226.77 pounds. So those are my answers. Now the last thing I need to do is to just go compare this number to see if it exceeds the tension that's required to get the package moving. Because if the package doesn't move, then there's not a problem. There is no problem. I don't mean there's not a problem like this, it's not a problem. I mean we don't have a problem to work at that point. So is 226 greater than 43? Yes. So we're good to go. Okay. Now there's a little difference here because with the 43, we used mu s, and for the tension that we actually calculated, it's mu sub k. So the actual tension that we would compute would be lower in the second case. But so the only time that this becomes an issue is if those two values are extraordinarily close. Okay? Or if the difference between the static and kinetic coefficients, the static and kinetic friction coefficients are significantly different. They're usually different by 10 or 15%. So in that case, all of this works. Also because the second tension is higher, it would work anyway. But if it was close, like if I calculated this tension to be 40 pounds, I would have to go back and redo this process to make sure that I wasn't blowing smoke, so to speak.
Yeah.
Yes?
I got the tension to be like 199.67.
Oh, yeah.
The acceleration was like 9 and 4.5.
Yeah.
Way different.
Well, not really. I mean, it could be, but,
It's kind of close, but not so.
right. Is it? Okay. Should we take a look at where your differences were?
I have my math. I did it.
Yes.
I can check it. Do you want to see?
Sure. Let's take a look and see what you have. And sometimes it's hard to say, your numbers could be different if we, do you mind if I put it up on the,
That's fine.
on the viewer? Okay, let's take a look here.
No, you can't read it. I'm sorry, guys.
No! It's all, oh, that's okay. All right, so we're talking about this problem. You have a 200-pound block. You have your 200, your normal, up the direction. What is the 175?
It's from problem 12.13.
Okay. Well,
Or did I not do that right?
no, it's possible. I just couldn't,
See that one on my version.
What's that?
I think me and you actually have the same version of the book, and I don't see a 170 or whatever.
Right. I think that's what it is. So if we look at 113, we're talking about the acceleration and the tension. So the thing is that we really don't know the tension here. In other words, the tension in 1213 and 1214 are not going to be the same because the friction is going to change the value of tension. So you can't assume if you calculated 175 without tension, the tension is going to be different.
So then we should have the same answers.
Yes,
I,
I
did
hope
this
so.
Very wrong.
No, your work looks really good. Your work
Thanks.
looks right on track. But yeah, that's the only difference that I see is that basically when you carry over from problem 13, because there's no friction, if
I
you look
can't
at that
carry over the
exactly,
tension?
that's
That's not
exactly
bad.
right. See, there you go. But you're set. Aside from that,
I just have
yeah,
to
and it kind
erase
of
all
makes
this.
sense. No, but it also kind of makes sense, doesn't it? If you think about it, if there's no friction, you're not going to have to
Yeah.
pull as hard on it to make it move. All you're really overcoming is the weight along the plane. Excellent questions. That is super. Do you guys have other questions, comments?
I tried to do 12.36 how you explained it, but I kind of just got lost.
Okay. So let's go ahead and take a look at 12.36. Okay. And I had told, Logan had come in to work with me a little bit earlier, and not everybody draws this series of little pictures. That's something that I have found very useful, and just to break it up into little tiny pieces. Because otherwise I get sort of distracted by the other information. So if you like to do that, I have found it to be effective. And a lot of my students have also found it to be effective, but it's not a requirement. A lot of people do these in one gigantic picture. So when I do it that way, it's for clarity for me. And so you may find it useful or you may not. So let's take a look at 1236. We have a tether ball, and it weighs, has a mass of 450 grams. So this is what we have. We have the tether ball pole, and it goes from the top at B to C, where it's in the ground. And we have some length of a tether, and then we have the ball that has a mass of 450 grams, which of course would be 0.45 kilograms, right? Now, we are told that the length of this string is 1.8 meters, the length of the tether, right? And then we're told that the person who is hitting the tether ball is keeping it in a beautiful horizontal circle. So in other words, everywhere in that horizontal circle, the result of that circle being totally horizontal, in other words, the ball's not going up and down, it's not getting closer and farther from the pole, the fact that it's in a horizontal circle tells us that everywhere the angle is going to be, whatever the angle is, theta is constant, right? All right, so 450 gram tether ball, moving horizontal circular path, constant speed. The velocity of the ball is 4 meters per second. Okay? Determine the angle theta that the cord forms with the pole and the tension in the cord. So we want to know theta, which, like I said, just by analysis, I shouldn't say just by analysis, but by analysis we know that theta is constant. All right, so this is a picture looking at it from the side view. Let's look at the ball from above. If the ball is following a circular path, that tells us that this value is some sort of center of curvature, that we have a tangential component of velocity and acceleration, and we have that normal component of velocity and acceleration. Now, the normal component of acceleration, or the force, is directing it outward. What's keeping the ball in the circle? It's the tether, isn't it? It's the tension in the tether. So that means that we have some component of the tension operating to pull it toward the center of the circle. So this sort of a force that pushes out is referred to as a centripetal force, and we know it's there because of the effect. We can also think of it, instead of being a centripetal force, as being an acceleration directed toward the center. So if we do it that way, we can say that the tension along this, the component of the tension in the circle, is going to equal the mass of the tether ball times the acceleration of the tether ball in the circle. And we've just determined that the acceleration is actually going to be that normal component of acceleration. And we know from our previous discussion that that's equal to v squared over rho. Okay, now, but here's where we have to use a little bit of trig. We have to go back and forth between this picture and this picture. When we talk about the component of the tension that's in the circle, if the entire tension is directed along this angle theta, or not theta, it's going to be 90 minus theta rather, is the angle between the tether and the circle, isn't it? Or we could say that the component of tension in the circle is the entire tension times the sine of theta. So you could say T times the sine of theta, whatever it might be, is equal to mv squared, which we know, over rho. Well, let's think about what rho is. We know that this is 1.8 meters, don't we? And we know that this angle is some theta. We don't know what it is. But we could say that rho is going to equal 1.8 meters times the sine of theta. So far, so good? All right. So then we get T sine theta equals mv squared over rho, which is 1.8 meters times the sine of theta. Okay.
Is this where you want to plug in the M and the V?
Yeah, exactly. The thing is that we're going to, this is going to be a sine squared function, so it's a little, it's not, I wouldn't say tricky, but I was trying to think if we're going to have another equation that's going to help us out, or if we're going to have to just, well, we could do it in the, okay, let me just think about something. So if we do this, we would have T, when we would have 1.8 T times the sine squared of theta equals mass times velocity squared. And we know both of these is what Logan is getting at. So we know that the mass is 0.45 kilograms, and we know that the velocity is 4 meters per second. So if we square that entire thing, we're going to get T sine squared theta is some sort of a constant, right? But what else do we know? Well, let's take a look at the tether ball in the other direction. The tether ball is being pulled up at this angle, and it's also being pulled down. Its weight is pulling it down, right? So we have another equation. If this is theta, we can say that in the y direction, t times the cosine of theta minus the weight, and since it's staying in that vertical or that horizontal circle, there's no acceleration, so that's equal to 0. So we can say that t cosine theta equals the weight. Weight is 0.45 kilograms times 9.81 meters per second squared. So we get a constant is equal to t. And we have this function. So we're going to have t's and sine cosine of theta. So there will be a unique solution to that. What it is, that is another question. But do I have enough time? I have 4 minutes. So let's see what I can get done in 4 minutes. So if I take the mass of that ball, 0.45 kilograms, and I multiply it by acceleration of gravity, I get its weight. So this is 4.415 newtons. So t times the cosine of theta equals 4.15 newtons. Up here, I know that t times the sine squared of theta equals 16 times 0.45, which is 7.2. And that's kilogram meter squared per second squared. So that's a Newton times a meter, if I'm not mistaken. All right, so now how you want to solve this is another question entirely. I could set this equal to, I could say t then is equal to 7.2 over the sine squared of theta. And I could here say that t is equal to 4.415 divided by the cosine of theta. And if I set those two things equal to each other, okay, and so then, in other words, you could say you need to find the angle where the cosine of the angle is equal to 4.415 times the sine squared of the angle divided by 7.2, or you can say that divided by 0.415, 1 over, equals, so the cosine of theta equals 0.61319 times the sine squared of theta. All right, so you're going to have to use an equation solver. That's not something that you can solve for explicitly. You could say the inverse because, in other words, there's a cosine on both sides, but there's going to be a unique solution to that. So you could use an Excel spreadsheet, you could use an iterative function, you could use an equation solver and determine what theta is. And then after you find theta, you can plug that back up here and find tension. And then you have both of the things that you need to find. How's that? There may be an explicit solution that I have. I mean, there is an explicit solution, but you just have to do an equation solve to do it because the two variables are, the cosine is on one side and the sine is on one, but those are related. They're dependent on each other, right? So there will be a solution, but you can't solve it algebraically. All right?
Is there any way you can use like some kind of weird trig function? And
Yes, that is quite possible, right? So if you have a weird trig function, that would be super. If you have an equation, but like I said, with things like this, if I don't have anything else at hand, I'll do Excel, and I'll make a list, 0 to 90, and I'll find where it changes. You know, it's like you calculate the right-hand side, calculate the left-hand side, till it starts to converge, and then I'll sort of converge on that. That is sort of the brute force method, but it works. So that's one of the tools available to you. All right, do you guys have any other questions? Well, we did not get into section 12.2, doggone it, but we will next time. So, darn. Yes, it did. It did. And I promise you I will never give you like 14 problems to do at night because they are very time consuming. So, all right. All right, well, you guys have a great weekend. And we'll talk to you. Well, I'll be here Monday. So if you need me, come on by. Otherwise, we'll see you Wednesday.